Right now, in this video, we have this very first question on the board. Okay, the question is based on font series. Now let's work on it together and see. It's a simple and interesting one. The font series of lines in the emission spectrum of hydrogen corresponds to the transition from higher excited state to the ground state. Calculate I, the wavelength of the fifth line. I, what is the energy of the electron which drops from the fifth to the second line? Now we are to take the Rydberg constant as 1.0974 times 10 raised to power 7 per meter. How do we approach this question? The first thing we need to remember is that this problem is based on font series, and because it is based on font series, we need to quickly determine the N1 value for font series. Font series is number 5 series in the hydrogen spectrum. So I'm going to say that we are to get the wavelength. That's the first part of the question. The wavelength of the fifth line we don't know. Wavelength of the fifth line we don't know. Then we know that N1 is equal to 5 for font series. For font series. For font series, N1 is equal to 5. So what do? We are going to quickly discover the value of N2 since the excitation was from the fifth line. Is that okay? So the fifth line, the N2 value that we need to know that. And of course that will lead us to do a little sketch. Let's sketch. Let's take care to be the ground state N1 equal to 5 for the font series. And if that is the case, then we're going to have 5 lines drawn above it. Quickly, 1, 2, 3, 4, 5. So this is the fifth line. Now if this is the fifth line, can we determine the value of N2 in each case? For the first line here, have that N2 will be equal to 6, of course, because N1 is 5. Then the second line, N2 will be equal to 7. The third line, N2 will be equal to 8. Then this, N2 will be equal to 9 for the fourth line. And then the fifth line, N2 is equal to 10. Now we've obtained the value of N2. I hope you see how sketching that gives us the value of N2 quickly. So you can say that here N2 is equal to 10. Now we're going to recall the Rydberg equation that to get wavelength, one of our wavelengths is equal to the wave number and is equal to the Rydberg constant, open bracket, 1 over N1 squared minus 1 over N2 squared. This is the Rydberg equation. Now this equation gives us the value of the wave number, V bar here directly. So once we get the value of the wave number, we take its inverse to determine the wavelength. Is that okay? So I'm going to write that it implies that wave number is equal to the Rydberg constant 1.0974 times 10 raised to power 7. That's going to be multiplied by 1 over N1. We have the value to be 5 for font series. We square it, then minus 1 over N2. We obtain it to be 10. We square it. So we've done this, right? Let us now reach out for a calculator and see what we're going to get. The V bar value is 1.0974 times 10 raised to power 7. And then that is 1 over 25 minus 1 over 100. So we're going to press that straight ahead from the calculator and see. Or from here, it's giving me 0.03. 0.03. So this is equal to 1.0974 times 10 raised to power this. Then multiplied by 0.03. Is that okay? That 0.03 is the same as 3 times 10 raised to power minus 2. In fact, let me show it here because I'm going to use standard form to work it out quickly. 3 times 10 raised to power minus 2. That being the case, I'll multiply that 1.0974. I'm going to multiply by this 3, so times 3. From here, it's giving me that the wave number is equal to 3.29. Then times 10 raised to power. You deal with the power. This is 10 raised to power 7. This is 10 raised to power minus 2. Pick one of the 10s and then you add your power. So 7 plus minus 2 will give us 5. So that's the value of the wave number. And of course, the wave number is going to have the unit of the Rydberg constant. And what's the unit? Per meter. Per meter. So we've gotten the wave number. We can now reach out for the given, that's the value of the wavelength for the fifth line. So it implies that the wavelength for the fifth line will now be equal to 1 over the wave number. Remember I explained something. 1 over lambda is equal to 1 over V bar. So since I know the value of my wave number, I'm going to cross multiply then make the lambda subject of the formula. This is 1 over 3.29 times 10 raised to power 5. If you work this out, our lambda is going to give us what? Let's find out. 3.04 times 10 raised to power minus 6. The unit of wavelength is meters, alright? It's meter because it's inverse of the unit of wave number. And of course, this is the value of the wavelength for the 5th line in the font series. Now I want to look at the second part of the question where we are required to determine the energy of an electron which drops from the 5th to the 2nd line. Now, how do we accomplish this task? Is that okay? We are to determine energy, you know. So the first thing you need to remember is the fact that we already established in previous video that the energy of radiation, the energy of a photon is equal to HF, and that F is the frequency of that given what energy level. Now, this is the energy difference for this question between the 5th and what? The 2nd line. So we should be expecting to apply the formula here on the board. So we're going to write the second part of the question. The energy change, which is now going to be E5 minus E2, will be equal to HF5 minus HF2. So this is going to be the formula we would use. You remember where we established one formula, En minus EO equal to HFN. Alright, that En is the energy level of the higher state, then E0 was taken as the energy level of the ground state. But in this case, this quantum drop is between 5th and 2nd line, and that's why we have to take into account the frequencies of these two lines. H there is the Planck's constant, of course, 6.6 times 10 raised to the power minus 34 joules seconds. So it's a constant, we don't have problems with that. For this question now, it's expected that we should know the value of F5. We should also know the value of what? F2. Is that okay? And of course, you know, we can still write this equation as H, open bracket, F5 minus F2 by factorizing the H. So let us go and determine the frequency of the 5th line and the frequency of the 2nd line. And what will help us to do that? So we can say for the frequency of the 5th line, we want to recall that frequency is equal to speed of light divided by what? The wavelength. Is that okay? So to get the frequency of the 5th line, it implies that frequency of the 5th line is equal to speed of light. Of course, the speed of light is 3 times 10 raised to the power 8. Although it wasn't given here, but take note, these are constants. Is that okay? They are constants. Ordinarily, it's meant to be quoted in the question here. But in the case where it is not given, as much as you can remember that, it will be pretty good. So, speed of light divided by the wavelength of the 5th line. So, that's going to be 3 times 10 raised to the power 8 all over. The wavelength of the 5th line, we got it to be 3.04 times 10 raised to the power minus 6. So, the frequency now of the 5th line would give us what? Let's find out. 3 divided by 3.04. So, 3 divided by 3.04 would give us 0.999 approximately, 0.99. So it's going to be times 10 raised to power times 10 raised to power 14. So this would be equivalent to 9.9 times 10 raised to power 13 hertz. So this is the frequency of the 5th line. We shall do same to obtain the frequency of the 2nd line. But you know, in this case, we do not know the wavelength of the 2nd line. So we have to go and find out the wavelength of the 2nd line quickly. Is that okay? So I'm going to write for F2, obtain lambda 2 first. So that's what we should do. So we're going to go back to write back the equation. I'll be very fast in doing that. Take note, for the 2nd line, we are dealing with font series. Font series, the ground state N1 is equal to 5. So the 2nd line will give us what? 7. Is that not so? To give us 7, remember the line we sketched. So let us do that and see. It implies that 1 over lambda is equal to the wave number equal to right back constant, open bracket, 1 over n1 minus 1 over n2. That is the right back equation. So we're going to substitute first. Let's get the wave number for the 2nd line. Is that okay? Wave number for the 2nd line. That's going to be equal to R, and R there is 1.0974 times 10 raised to the power 7. Going to multiply by 1 over 5 squared minus 1 over 7 squared. N2, like I stated, for fund series, the second line is equal to 7. So this is going to give us, all right, let's see, going to press all of them together at the same time to see what it's going to give to us. So this is 1 over 25 minus 1 over 7 squared is 49. Good, that is 0.0195 and then 9, it continues. So I'm going to multiply this value. Okay, let me still punch that again, please. 1 over 25, then minus 1 over 49. Good. So I'm going to multiply this by 1.0974. Okay, so from here, what I obtained from this bracket, I multiplied it by 1.0974. And it gave me 0.0215. So I'm going to multiply by 10 raised to the power 7, which eventually becomes, moving these points 2 times. Is that okay? It's going to give us 2.15 times 10 raised to the power 5 meters. So this is the wave number of the second line. So it implies that the wavelength of the second line would give us 1 over this wave number we calculated, 1 over 2.15 times 10 raised to the power 5. So doing that, the wavelength of the second line is equal to, okay, wave number, the unit is per meter. So let's put that. So 1 divided by 2.15 times 10 raised to the power 5. So it's giving me 4.65 times 10 raised to the power minus 6 meters. So this is the value of the wavelength for the second line in the fund series. Is that okay? We can now obtain F2. So it implies that F2, that is the frequency of the second line, speed of light, divided by the wavelength of the second line. If you substitute, you have 3 times 10 raised to the power 8, divided by the wavelength of the second line, which is 4.65 times 10 raised to the power minus 6. If you do that, the frequency of the second line will be equivalent to, let's find out, 3 divided by 4.65. 3 divided by 4.65 gave me 0.65. Then times 10 raised to the power 14. This is equivalent to 6.5 times 10 raised to the power 13 hertz. Alright, so this is very good. We've obtained F5 and F2. We are now set to substitute them into this formula and get the value of the energy that is being radiated when the electron fell from the 5th to the second line. I'll be going for a short break. When we're back, we'll do that. Now you're welcome from the short break. We now want to determine the energy of the electron which dropped from the 5th to the second line of the fund series. Before the short break, we already obtained the frequency of the 5th line to be 9.9 times 10 raised to the power 13 hertz, and then the frequency of the second line to be 6.5 times 10 raised to the power 13 hertz. So we're going to substitute it into the equation that the energy change is equal to E5 minus E2. Then that is equivalent to the Planck's constant F5 minus what? F2. Because we know the Planck's constant, the value is 6.6 times 10 raised to the power minus 34 joules second. So we're going to fix that up, 6.6 times 10 raised to the power minus 34. Like I stated, normally these constants were meant to be given in the question. The Rydberg constant, the speed of light, the Planck's constant. Is that okay? So have that in mind. But there is no harm, as much as you can, memorizing these constants. Is that okay? They are standard. So as much as you can, please memorize them in case. Alright, in case it's not given, you use it, okay? Let us now multiply this by the frequency change. F5 is 9.9 times 10 raised to the power 13, then minus F2 is 6.5 times 10 raised to the power 13 hertz. So we're going to include that in brackets and see what we're going to solve here. This will give us 6.6 times 10 raised to the power minus 13, minus 34 rather, then multiply by. When you come to this bracket, how do you work that out? 10 raised to the power 13 is common to the two terms in the bracket, so we're going to subtract this 6.5 from 9.9. So 9.9 minus 6.5, the result is 3.4. 3.4. We factorize 10 raised to the power 13, so we'll pick one of them, 10 raised to the power 13. Then this energy of the electron will now give us, let's multiply 6.6 by 3.4, and this gave us 6.6 times 3.4, it's giving me 22.44. 22.44, then times 10 raised to power minus 34, you add it to 13 using the law of indices. Minus 34 added to 13, it's giving me minus 21. So this is the energy, or you can choose to say that the energy change is equal to 2.244 times 10 raised to power minus 20. Of course, you know, I move the point once to the left to get 2.2, so I'm going to add that one time to the power, and then minus 21 plus 1, you know, it's going to be minus 20. So this becomes the value of the energy of the electron, which dropped from the 5th line to the 2nd line of the Fund series, 2.244 times 10 raised to power minus 20 joules. So you see, that's how we approach this question. Now we have this second question on the board. What is the number, that is wave number, and wavelength of an electron which was excited from bound series to bracket series? We're giving right back constant here, 109737. But look at the unit per cm. Is that okay? You have to test your zone of proximal development. Determine the energy of the electron in the transition in question 2 above. So determine the energy in this transition, you know. Take the speed of light to be 3 times 10 raised per 8 meters per second, and then Planck's constant at 6.26 times 10 raised per minus 34 joules second. How do we solve this problem? Looking at this, we want to consider that the excitation is from Balmer to what? To bracket series. So since it's from Balmer to bracket series, suppose I take this and this to be the two series. So there is this jump upward like this. This is Balmer, this is Balmer, and then this is what? Brackets. Is that okay? So there was no specification of the line the thing jumped from in Balmer and where it jumped to in brackets. No specification. And because there is no specification, it means that N1 will be taken as the ground state value of Balmer. You're going to say that N1 is equal to, Balmer is 2, you know that. And then N2 will be taken as the ground state of bracket series, which corresponds to the N1 value of bracket. So I will come here and say that N2 is equal to N1 of bracket, and the value is what? Bracket is number 4, we know that, isn't it? In fact, let me remove this N1 so you don't get confused, okay? Let's just leave it as N2 equal to 4. The ground state of bracket is 4, we know that. So having said that, we're going to recall the right back equation that 1 over lambda is equal to the wave number, that is right back constant, 1 over n1 squared minus 1 over n2 squared. So let us obtain the number. Is that okay? Let's obtain the number. That is the wave number of the electron. So it's going to be 109737, open bracket, 1 over n1. The value of n1 is 2, so I'm going to square it, minus 1 over. The value of n2 is 4, I'm going to square it. Now you notice that I didn't do any conversion here. I used the per cm value, and then my result would carry obvious centimeter, we know that. So this is going to be 1 over 2 squared is 4, then minus 1 over 4 squared is 16, we know that. So multiply that value from here, it's giving me 0.1875, so I'm going to multiply it by 109737. Alright, so the value here is 20,575.69. Remember, the unit will be per cm. If you want to convert this thing to meter, this per cm means divided by 1 centimeter. And 1 centimeter, you know, you can convert to meter by dividing that 1 centimeter by 100. We know that. Is that okay? So if this is per cm, look at what I mean. If you see per centimeter like this, means 1 over centimeter. That's what it means. 1 over centimeter. So this is the same as 1 over 1 centimeter. So if I'm to write this thing, okay, let's just do the calculation once. This is the same as, this is the first part of the results, or I can place the result as in meters. It's going to give me, so let's say that this is 20,575.69. You see, this per cm means divided by 1 centimeter. Divided by 1 centimeter. That's the meaning. Is that okay? And that will be equivalent to, I can now convert this to meter. It's going to be 20,575.69. To convert centimeter to meter, you divide that given centimeter by 100. So this is what we're going to get. Now, mathematically, you know that centimeter value, which is 1 over 100, you know, this 100 will go up. If it moves up, it will become 20,575.69. I'll multiply it by 100. So doing that, let's see, 20,575.69. So times 100, let's see what it's going to be. So from here, it's giving me 20, that is 2,057,569 per meter. So this is an alternative result to that in meters. Is that okay? Take note of that. You can put it in standard form. In standard form, this is 2.057569 times 10 raised to the power minus 6. Is that clear? Okay, now can we go for the wavelength? Because we've known the wave number, let's go for the wavelength. Let me put, say, answer here. And as an alternative, we also have answer here. So we'll have the wavelength now. So for wavelength, we're going to recall that wavelength is equal to 1 over wave number. And that's going to give us 1 divided by, you have the choice of using any one of these two. If you use this, then your wavelength will be in centimeter. If you use this, your wavelength will be in meter. Okay, let me just use this one we obtained. That's 20,575.69. So let us see what it's going to give to us as wavelength. 1 divided by 20,575.69. So from here, it's giving me 4.86 times 10 raised to the power minus 5. The unit will be cm. So this is the result of the wavelength in centimeter. You can put it alternatively, or the wavelength in meters is going to give you what? In meter, you're meant to divide this centimeter directly by 100. To convert from centimeter to meter, we stated you need to divide the given centimeter by 100. Dividing this by 100 is the same as multiplying it by 10 raised to the power minus 2. Is that okay? And if you multiply this by 10 raised to the power minus 2, it's going to be 4.86 times 10 raised to the power minus 7 cm. Is that okay? No, not cm again, but meters. So we've converted the result to meters. And this is the value of this problem. That's how we approach it. So test your zone of proximal development place. Determine the energy during this quantum jump. And of course, you know how to do that. Get the frequency of what happens in the Balmer series at this point. Then get the frequency at this point. Is that okay? And then find the energy difference.